Today we'll be going through the Level 3 Physics Electrical Systems paper for 2023. So I actually sat this paper last year and I got an excellence, so I'll just show you guys what I did to get that grade. Question 1. Kate is learning about capacitors. She investigates a capacitor found in a camera. The capacitor is labelled 185 nanofarads. So because it's got the symbol F, we know it means capacitance, so we'll label it C. The camera also contains a 1.5 volt AA battery. Going to label it V for voltage. Show that the energy stored by the capacitor when it is fully charged by connecting it to the battery is 2.08 times 10 to the power of -7 joules. So what we're going to do is just prove that that is the answer. So what we're going to do is going to plug in our formula for energy for a capacitor, which is E equals 1/2 QV. So right now we've got the values for V and C. However, this formula requires Q and V. So what we're going to do is plug in our other formula, Q equals CV, and we're going to substitute Q for CV in this formula, which will get us the equation of this. So that means E will now be equal to 1/2 of CV squared. So all we're going to do now is plug in our values as such, and we should get the answer of 2.081 times 10 to the power of -7 joules, because this is 4 significant figures right there, and then they've asked for 3 and they've showed 3 throughout the question. We've got to round to 3 significant figures, so that is our answer here. Okay. The diagram below shows that the circuit used to charge the capacitor, the battery has an internal resistance of 0.27 ohms. Label it R for resistance. Assume the rest of the circuit has no resistance. So then again, they're showing us the capacitance and the voltage and our resistance there. Sketch a curve by plotting at least 4 points on the grid opposite to show how the charge on the capacitor plate varies with time once the switch is closed. Your answer should indicate the time constant for charging the capacitor and the maximum charge that will be stored on the capacitor plates. Okay, so we know that once the switch is closed and the current is flowing, charge builds up on the capacitor plates. So over time, charge on the plates will increase that type of thing, like that, and that's time on the bottom there. So it'll look like that. So they've asked for the time constant for charging the capacitor. So whenever you see a question about time constant, just plug in the formula T equals RC, and then we can plug in our values for R and C, as shown here, which will give us the answer of 4.995 times 10 to the power of -8 seconds. So once again, the question's 3 significant figures, so we round the answer to 3 significant figures, which will give us 5 times 10 to the power of -8 seconds. So when a capacitor is charging, it charges 63% of its full potential every time constant. So we now know that every 5 times 10 to the power of -8 seconds, the capacitor plates will be fully charged by an additional 63% of the remaining charge. So answer the first bit. So now we just need to show the maximum charge that will be stored on the capacitor plates. So that is Q equals CV, so that's charge. Plug in our values, which is that. Get us the answer of 2.78 times 10 to the power of -7 coulombs. But that's times to the power of -7. And the graph below, they've done it times 10 to the power of -8. So that is different to this one. So what we're going to do is shift the decimal point to the right once. So we'll get the answer of 27.75 times 10 to the power of -8 coulombs. So I've also just used the unrounded answer just so our future answers will be more correct. Okay, so now we know that's the maximum charge on the capacitor plates. We need to find the charge on the plates every time constant. So the first step, first time constant is the maximum charge times by 0.63. So that gives us the answer of 17.5 times 10 to the power of negative 8 coulombs. So what we do is remember that 17.5, 2, 4, 6, 17.5 is about here, and our time constant is every 5 times 10 to the power of negative 8 seconds, so that's our first point there. So next, second time constant. So because the capacitor plates it charges an additional 63% on the remaining charge. So what we're going to do is take our maximum charge, which is 27.75, then we're going to minus the first time constant, 17.5, from that value, and then we're going to times that by 0.63. So what we get is, within the brackets, is, and times that value is 6.49 times 10 to the power of negative 8. We then plus that onto the existing value of 17.5, which will then get us 24 times 10 to the power of negative 8 coulombs. So once again, we mark that on the thing, on the graph, sorry, and right there. Cool. So we'll do the same thing again. The maximum value minus the previous value, for this value here, times that by 0.63. That value right here, plus the existing value of 24 times 10 to the power of negative 8 coulombs equals 26.4. So once again, mark it up. 26.4, about there. Cool. And final point, because they've only asked for at least 4 points, so you can do more, but it's easiest just to do the minimum. Okay, same thing again, maximum minus the previous times 0.63 gets us 0.882 times 10 to the power of negative 8, plus that by the existing 26.4 times 10 to the power of negative 8 will equal 27.3 times 10 to the power of negative 8 coulombs. So find that on the graph, 27.3, a little bit further up, just about there. Cool. Now all we're going to do is connect the dots. That. No, let's redo that. Should be like that. Cool. Yeah, so just make sure it meets all the dots, like that bit there. Cool. Although the capacitor plates are rolled up, they act like two metal rectangles measuring 3.2 times 10 to the power of negative 2 meters times 1.83 meters. So here they've just given us the length and the width, so we know that it means that is area. Okay, with the dielectric material in between. If the dielectric material in the capacitor has a relative permeability of 2.10, calculate the distance between the metal rectangles. So this is just a quite simple, straightforward question. Just going to use this formula that we're given, where it's capacitance and the permeabilities times area divided by distance. All we're going to do, plug in our values, which we found earlier in the question as well. This value here, 8.85 times 10 to the power of negative 12, is the relative permeability of free space, I believe, but they give it to you on the formula sheet, times it by that value there, and then by the area, which is that stuff there, and then divide by distance. And then you just solve for D, and then just chuck it in there. So that's your answer to 3 significant figures. Cool. Question D. The charged capacitor can be discharged through a lamp by pressing a switch. In the camera, the lamp flashes when a picture is taken. Kate fully charges the capacitor with the 1.5 volt battery, but when the bulb is connected, it barely glows. Inside the camera, she finds wiring that allows the capacitor to be charged at 200 volts. Explain how this arrangement allows for a much more powerful flash. In your answer, you should show how the energy stored in a fully charged capacitor at 200 volt compares, I'm going to use that word in our answer, with 1.5 volt. How the higher voltage increases the initial current from the capacitor when it is connected to the bulb, and how the brightness of the flash will be affected by the higher voltage. Okay, so first step is to show the comparison of the energy with the two different voltages. So just use our formula here again from question 1. Going to plug in our values, same thing as before, but this time it's 200 instead of 1.5. So now we get the answer of 3.7 times 10 to the power of negative 3 joules with the 200 volt battery. Okay, so next we'll just write a paragraph which will answer the stuff. The original energy stored equals 2.08 times 10 to the power of negative 7 joules, compared, that word there, to a new energy stored equals 3.7 times 10 to the power of negative 3 joules. So just answering that first question there. As the voltage in the circuit is significantly larger with the 200 volt battery, there will be a larger current flow as I equals VR and the internal resistance is constant. So this is just the V equals IR formula, just rearranged to find I. Therefore, the initial current flow of the circuit will be much greater with the 200 volt battery opposed to the 1.5 volt battery. Cool. So that answers the second point, and how the brightness of the flash will be affected by the higher voltage. Cool. As the brightness of the flash depends on P equals IV, which is the power formula, when the lamp has a larger voltage, the power supplied to the bulb will be much greater and thus resulting in a brighter flash. Yeah, so that just answers that point there. That's really all you need to say. And this is why the circuit with the 1.5 volt battery will not provide a flash as bright. So just looping back around and just summing it all up really.